Breanna McGowan, and this is my Lab M01 video report. My objective in this lab is to analyze the two-dimensional motion of an object attached to a spring and assess the change in spring potential, gravitational potential, and kinetic energy, as well as the total change. I will look at the impact on both x and y axes of motion and calculate the period t of the oscillatory motion. My conclusion at the end has been that through this lab I have come to find the total change in energy in the system involving the mass, earth, and spring to be equal to 0, and I have come to understand how the motion is affected, which I will explain. And this all also involves modeling motion through PHYS. So here's a video that I was to analyze, and as you can see, it's a mass attached to a spring. I first went through and I calibrated the length and the mass and everything, and then I went through and got the points as it went through the point mass. And here you can see that it's an oscillatory motion, and so then I put the x and y information into an Excel spreadsheet and saved it as a CSV data file so I can use that in PHYS when I'm later modeling my motion. So I set all my conditions with the initial position here, as well as putting in the CSV file and changing the relaxed length, which is 0.126 LO, and then I changed the time step and how long the time is and everything in the rate so it would all be relevant. So first I'm going to be graphing the position y versus time. So here's the motion. Here you can see the model is the orange ball and then the actual observed motion is the blue ball. And I printed what the T of oscillation is. Here you can see I used the formula, and that came through 1.52 seconds. Now I'll do the same thing for the x motion, so I change it to the position x. And there you see it's the same motion and just graphing it differently. Again, the period was 1.52 seconds. So now I'm going to take a closer look at the graph for the y position. And here you see the red is the model, whereas green is the observed. You see that it's more up and down with the model, and then the green is slightly less extreme. And again, the period is 1.521 seconds, and the data for x is a little more radical, not as uniform, because it's only taken into account position y in this. And so the time again is 1.52 seconds. So then I graphed all the different energies to see how each thing was affecting the ball and vice versa. So here you can see I changed my plot to graph 4 different things. And so you have the red is the gravitational potential energy, the blue is the spring potential energy, the green is the kinetic, and yellow is total. So I came to calculate that the spring potential energy is and the delta KE plus delta UG will be equal to 0, so the spring potential energy is negative 0.0148, and the delta KE plus delta UG is 0.0144. And you can see on the graph that the total energy change is 0, which makes sense. Energy is always conserved. And in this system of the mass, spring, and the earth, there is no work done by the surroundings. So this makes sense because you have delta E equals the energy of the internal, which is equal to 0. And then going back to the period of time t, they don't differ, which also makes sense because the formula doesn't depend on the position of it. It's just no matter how far you pull or whatever, it's just going to be the same. So then I was posed with the question of if the initial position was set to the origin, which was at negative 0.7, how would that affect all the energies and everything? So I ran it. And you see that if you're starting at the same position, then nothing's really happening. So you have the potential and the spring potential energy. The potential energy remains the same because you still have all the forces acting on it. But there's not going to be any kinetic energy. And so you see there's the green lines right along the x-axis. And again, the total change in energy which is the yellow line, is equal to 0. So it all makes sense.